In this video, we will learn how to write an equilibrium product constant. So in the previous video, we defined equilibrium to be when the rate of the forward reaction was equal to the rate of the reverse reaction. But equal rates does not mean equal concentrations. We have to differentiate between rate of reaction and our proportions of reactants to products. We know that when we reach equilibrium, our concentrations of reactants and products don't change. So if we think about the course of a reaction, early in a chemical reaction, we start off with a lot of reactants and no products at all. And then as time progresses, we form more and more products, and our amount of reactants gets used up, until eventually the concentrations of products and reactants don't change anymore. And so once these lines flatten out, then we have reached equilibrium. But in this case, we can see that there are more products than reactants. But how far apart these lines are really depends on the reaction itself. And so we could draw a similar graph where we use up our reactants and they taper off, and we form products and those taper off. And in this case, we still have less products than we do reactants. But we're still at equilibrium because our amounts are not changing. So both of these lines are flat, and so we're still at equilibrium. So we need to come up with some kind of constant, some kind of value that will tell us how much products do we have relative to our amount of reactants. So we have to come up with something. We're going to be using an equilibrium constant, and we're going to call that K, a big capital K. And that's going to describe how far a reaction will go. That's going to be how far towards the product side. How far towards the product side. And that's going to be different than our reaction rate, which describes how fast it will get there. And so we're going to stop talking about reaction rates and focusing on how far the reaction goes. So our equilibrium constant is going to describe how far we're going to go. It doesn't tell us how fast we're going to get there. So we have a general format for a chemical equation. So if we have this general formula of A plus B goes to C plus D, where these little lowercase numbers are stoichiometric coefficients. So all of these lowercase letters are the stoichiometric coefficients for the bigger uppercase letters. Then we're going to write our equilibrium constant, which is abbreviated KEQ. EQ stands for equilibrium. Then our KEQ is going to be a ratio of our products to reactants. And remember that anytime you see these square brackets, then that means molarity. So we're looking at the molarities of our products over our molarities of our reactants. So if we have a lot of products, then we're going to have a really big numerator and a very small denominator. But here's the interesting part. These stoichiometric coefficients become exponents. Our stoichiometric coefficients become exponents. And so you can look up equilibrium values in tables for the K, or you can calculate them. And they depend on temperature because, again, if we increase the rate of reaction, then we might end up in a different ratio of reactants to products. So here's some examples of our equilibrium constant. And so if we look at this balanced chemical equation, then we have our equilibrium constant is equal to my products, which is HBr, over my reactants, which is H2 and Br2. And since this has a 2 coefficient, then that value is squared. And those are multiplied together. So if we look at the box, then that can tell us how much of this HBr we have. We have mostly HBr and very little reactants. So we have mostly products over few reactants. And so since we're going to have a large numerator and a small denominator, then our K is going to be a big number. We could also have an equilibrium that is mostly reactants. And so here we have very few products. Over mostly reactants. And so since we have a very small numerator and a very large denominator, then our KEQ is going to be a small number. That means by looking at our KEQ number, we can decide whether we have mostly products or mostly reactants. So how big that K value is tells us whether we favor our products and we have mostly products, or if we favor reactants and we have mostly reactants. And if we have approximately equal amounts of reactants and products, then our K value will be close to 1. Now you might notice that this figure has a C here after the K. Let's talk about those subscripts in a little bit. We'll talk about those subscripts in a little bit. Okay, so let's take a moment and try to come up with some equilibrium constants by looking at some actual balanced chemical equations. And then we'll predict whether the equilibrium favors the reactants or if it favors the products. So in this, you can pause the video if you want to work it out on your own. Okay, I'm going to go over it. So we always have our products over our reactants. So let's start with our products. We have SO3, and we have a coefficient of 2. And in our reactant side, we have SO2 raised to the second power, so it's squared, times our molarity for O2. All right, I'm going to write the equilibrium expression for the second one, and then we'll talk about the values. So for this one, our product is NO2, and that's going to be squared because of the 2 coefficient. And then I'll take my molarity of N2 times my molarity of O2 squared. So that too became an exponent. All right, now let's look at the value. Since this is a positive exponent, that means that this is a large value. And so we have a very big numerator and a very small denominator. And so this one favors the products. And on the second one, we have a negative exponent. And so that negative exponent means that we have a very large denominator and a very small numerator. And so we have mostly reactants. So I'm going to write favors reactants. Okay, here's a practice problem for you. It says, which of the following is the correctly written KEQ for the following reaction? We have 2 potassium chlorates, which are solid, forming 2 potassium chlorides, which are solid, and 3 O2 gas. Go ahead and pause the video and try to work this out on your own. Okay, let's talk about this. You may or may not have noticed on the previous slide that solids and liquids do not appear in the equilibrium constant. Only gas and aqueous appear. And that's because our solids and our liquids are readily available, evenly distributed, most likely, in our chemical equation. And so it's really our gases and our solutions where we have to worry about how spread out they are and whether our reaction can continue to happen. So solids and liquids do not appear in equilibrium. So since we're trying to write out the equilibrium expression, let's go ahead and cancel out, cross out all of our solids and our liquids. Okay, so when we're writing this out, we have to remember that we have our products over our reactants. And so we are going to have our O2 raised to the third power over nothing. I can't have over 0 though, so that's going to be over 1. Over 0 is undefined, so that's going to be over 1. And anything divided by 1 is just itself. And so the correct answer is O2 to the third power. If this reaction was written in reverse, then, and we had only the O2 on the reactant side, then we would have D. So this would be like if it was on reactants. All right, so now it's time to talk about those subscripts that we can write. So there's a lot of different K's. And so anytime you see a capital K in this chapter, that means you write your equilibrium constant. And so you would write your equilibrium constant the same way with your products over your reactants. But you can have different letters after this K. And I don't want you to get tripped up over what letters are written as subscripts on this K, because they're all set up in the same way. So same general setup for all of them. Those little subscripts can be used to describe what it's an equilibrium constant of. So if you see EQ, that's a generic equilibrium. Kc refers to molarities. Kp refers to pressures. Kw, we actually saw that one in chapter 12. That's for water. And then Ka, A stands for acid, B stands for base, and then Sp stands for solubility product constant, and then Kf is formation. So these are inverses of each other. That's solubility is how much dissolves, and then Kf is how much solid forms. So those are opposites of each other. You'll be mostly seeing KEQ, KW, KA, and KSP in this class. So in the last chapter, we did talk about KW, which is the ion product constant of water. And so if we write out an equation of water reacting with water in an acid-base reaction, then we have, if this is an acid, it's a proton donor. And so we'll subtract an H plus and then add the H plus to our base. So we'll end up with OH minus, hydroxide ions, and H3O plus ions. That's aqueous, aqueous, liquid, liquid. Water is always a liquid. So let's write out the equilibrium constant for this reaction. We have Kw is equal to my H3O plus molarity times my OH minus molarity over water. But water's a liquid, and so we don't include it in the equilibrium constant. And so now we can look at that, and that's our Kw is equal to the hydronium ion times our hydroxide ion. And then the value for that Kw, that equilibrium constant, is 1 times 10 to the minus 14th. And so we can think about this minus 14th power now and realize that this is a very small K. That means we have mostly H2O molecules and a very small amount of products. And we can understand that if we change the value of H3O plus, then this is constant. It's always constant. It's always that value. So if we increase one value, then the other value has to decrease. Now, another application of K is this Ka. Ka can be an indication of acid strength. We know from earlier chapters that strong acids completely dissociate. That means they ionize in solution. So you have HCl and H2O. And so here's HCl. This is a strong acid. And so HCl and H2O, the water is going to accept the proton from your HCl, so that becomes H3O plus, and then the HCl becomes Cl minus. So if we write out the equilibrium constant for this, we know that HCl is aqueous, water is a liquid, so water won't appear, and then these two are also aqueous. So we have our products over our reactants, and that's equal, the KEQ for K value for that is 1.3 times 10 to the 6th. And so this favors reactants. Favors the products. Favors the products. Large value. And so that means that we have mostly our hydronium and Cl- ions. And so that is supportive of our idea that it completely disassociates. That's in contrast to our weak acids. Weak acids only partially ionize in solution, and that means there's very few ions. And so here's HF. HF is a weak acid, and much like before, that will form H3O plus and F minus. Liquids don't appear in the equilibrium expression, so we have our products over our reactants, and this is a very small value. And so small values of K mean that it favors the reactants. And so that means it favors being intact molecules with very few ions. So let's practice interpreting our value of K. Below is a table of Ka values for strong acids. Which acid is the strongest strong acid? Go ahead and pause the video and decide for yourself. Okay. Did you select HI? If so, you are correct. HI is the strongest acid. So this is the largest K, which means it's the strongest acid. Another way to think about it is that strong acids have to completely ionize in solution. And so if we think back to our periodic trends, then iodine is a much bigger atom than chlorine. And so this is a longer bond distance than chlorine. And so this is a weaker bond because it's longer. And you know the opposites attract. And so these electrons are very far away from the nucleus. And so they're not as closely bound. So that's a weaker bond, easier to break. And so you'll end up with your H plus ions and your I minus ions more often. All right. So we can also use this to figure out our equilibrium expressions for when we're dissolving ionic compounds. So when we're dissolving our ionic compounds, we have a solid that's turning into ions in solution in our net ionic equation. So we have this example has our solid silver chromate, and that means that we have 2 silver ions for every 1 chromate ion. And solids don't appear in the equilibrium expression, so we can just cross that out, and then we'll have our products. And so we have our chromate raised to the first power times our silver ion concentration squared. And so this is what we call our KSP value. And that will tell us how much is dissolved in solution. Equilibrium is reached when the rate of the solid dissolving is equal to the rate of it recrystallizing. So here's some different KSP values for ionic compounds. Remember that a large KSP means that it's very soluble, and a small KSP means not very soluble. So if we compare different compounds, we can compare let's compare lead sulfate to lead sulfide, since those sound very similar. And look at the exponents here. We have a very small exponent times 10 to the minus 29th power for our lead sulfide, and then our lead sulfate has a minus 8 exponent, which is not as negative. And so our lead sulfate is more soluble than our lead sulfide. So PbSO4 is more soluble than PbS. And we can tell that by looking at the equilibrium constants. These are all negative values, which means that they're all probably not soluble, or we would classify them as insoluble. But insoluble doesn't mean none dissolves, it just means a very small amount dissolves. Let's do a practice problem. I want you to write out KSP expressions for each of the following ionic compounds. Go ahead and pause the video and try to figure out what ions will form from each of these ionic compounds and write out the equilibrium expression for each. Okay, let's go over this. So in lead sulfide, sulfur is a 2- ion because it's right underneath oxygen. And then iron, we had 1 iron for every 1 sulfur, and so that means our iron has to be a 2+ ion. Aqueous, aqueous. And so our K value is going to be our products over our reactants. And so we have 1 iron, and then we have our sulfur ion. And then solids do not appear in the equilibrium expression, so we won't have a denominator. All right, let's deal with this next one. Our anion is carbonate. Whenever you're in doubt of what to start with the anion. All the anions have known charges. So carbonate's a 2-. We have 2 silvers. Silvers like to become +1 ions anyway. So each silver is +1. And so we have to make sure that we also remember this 2. That 2 is going to become a coefficient up in front. We'll have 2 separate silver plus ions. So now we can write out our K expression. It doesn't matter which order you write these in. You could write the carbonate first. That's okay. The important thing is that you square the silver ion concentration. And then again, solids do not appear. Now let's do this last one. In this last one, we have calcium, and then that's iodate. So calcium is 2+ ions. And then iodate is a 1- ion. And then we will have 2 iodates because of that 2 coefficient there. So that 2 coefficient goes up in front. So our K value will be equal to our calcium ion concentration times our iodate concentration squared.